So good evening, all of you. So once again, welcome to Physics by Physics. And in this session of PGT Physics practice session, we are discussing the fourth chapter, that is moving charges and magnetism. I have taken some question in last lecture. Now we will take other questions in today's lecture. So let's see. Let's start with question number 8. Let's start with question number 8. So let's see question number 7 also. Question number 7 is what? What is the magnitude of magnetic force per unit length on a current carrying a wire of 8 ampere, making an angle 30 degree with the direction of the uniform magnetic field? Uniform magnetic field means you have a wire in which current I is flowing, and let's say it makes an angle 30 degree. So what will be magnetic force? You know that magnetic force, question number 7. So this magnetic force is given by I L cross B. So L is always in the direction of current. So this is the direction of L. So you have to find the magnitude. So magnitude of F will be given by I L B sine of 30 degree. Simple question. And you have to find magnitude of force per unit length. So small f is F by L. So that is IB sine 30 is 1 by 2. Current is given 8 ampere. This is 0.15 Tesla divided by 2. So this is 1.2 by 2 Newton per meter, force per unit length. And then this value will be, this is 0.6 Newton per meter. This will be force per unit length experienced by this wire. So you have to see application of force on a current carrying loop. Clear? Now see next question. Question number 8. Question number 8. Now you have a two long parallel straight wires A and B. It's a very long wire A, another wire is B. Carrying current 8 ampere, this carries current 8 ampere, and this carries current 5 ampere. This is wire B. In the same direction, separated by a distance of, this is 4 centimeter. Estimate the force on 10 centimeter section of a wire A. What will be force experienced on this having length of 10 centimeter? So that force is given by, force experienced by wire A is given by mu naught IA IB. This is mu naught I by twice R into length L, because force per unit length will be this value. And this will be 2 pi also, because it's a case of a wire. So here you will get 2 pi r. And you know that when currents are in the same direction, they will attract each other. When currents are in the same direction, you will see they will attract each other. When currents are in opposite direction, they will repel each other. So mu naught is given by 4 pi 10 to power minus 7. IA and IB is IA and IB is 8 into 5, and L is given as 10 centimeter. Length L is 10 centimeter. This L will be 10 centimeter, and that is 0.1 meter. And this will be 2 pi. R is 4 centimeter, so that is 0.04 meter. So this will be the force. So let's calculate the value. This is 2 times, and then this will be 8 into 10 to power minus 7. 5, this will be 5 into 2 is 10. 10 into 0.1 is 1. Divided by 4 into 10 to power minus 2. So this will be 2 into 10 to power minus 5 Newton. 2 into 10 to power minus 5 Newton. So this is the force. If you have to find force per unit length, then it is mu naught IA IB by 2 pi r. R is the distance between these two wires. So when currents are in the same direction, they will attract each other. And when they are in opposite direction, they will repel each other. Clear? Now solve question number, let's see question number 9. See question number 9. Try to solve question number 9. So question number 9 is a long straight wire of circular cross section of radius A carrying a current I. The current I is uniformly distributed across this cross section. Calculate the magnetic field in the region R less than A and R greater than A. Question number 9. So you have a circular cross section. And this radius is A. And steady current I is uniformly distributed. So current I is uniformly distributed throughout the volume. So what will be current density J? This is given by current per unit area perpendicular to current flow. So total current is I. So current density, because it is uniformly distributed and this area is perpendicular to current flow. So that's why current density will be in the Z direction. And in this symmetry, if current is in Z cap direction, magnetic field is in phi cap direction. It has symmetry of wire. So if you want to find field outside any point P outside, so you have to consider this as an Amperian loop. And you have to see what is current crossing through it. So current will cross perpendicular to it. So for R greater than A, you know that close B dot dl is mu naught total current enclosed. So this will give you mod B into 2 pi r, and current crossing through this will be, because total current is I, so I'm directly writing with I. So B will be mu naught I by 2 pi r, direction is phi. So outside magnetic field is inversely proportional to r. This is outside point. And what will be magnetic field inside? So for inside point, let's consider any point P here. This radius is small r. So current density J and this direction will be what? Z cap. So an area element, they are in the same direction. So in this case, left hand side is mod B into 2 pi r. And what will be current crossing through it? Simply current density J into pi r square. This will be the current crossing through this loop. So you will get mu naught I by pi a square into pi r square. This pi will cancel out, this r will cancel out. So magnetic field B is given by mu naught I r by 2 pi a square, direction is magnetic field curl around it. So that direction is phi cap direction. Okay? So if you plot B versus R, radius is A, so it is proportional to R, and outside it is inversely proportional to 1 by R. So this is the magnetic field variation in when current is distributed uniformly throughout the volume. Is it clear? Now see next question. Just give me 1 minute. Now see, question number 10. It's a case of solenoid. Solenoid of length 0.5 meter has a radius of 1 centimeter, and it is made up of 500 turns. It carries a current of 5 ampere. What is the magnitude of the magnetic field inside a solenoid? So you have a solenoid here. So I am assuming, let's say, a wire is wounded in a helical form. Let's say this current is I. And I'm so its length is 0.5 meter. And its radius is 1 centimeter. Radius is 1 centimeter or 0.01 meter. So, because length is very large as compared to length is question number 10. Length is 0.5 meter and R is 0.01 meter or radius A is 0.01 meter. So what will be L by A? 0.5 by 0.01 meter. If you multiply with 100, so this is 50. So L is far, far greater than A. So we are assuming that it's a very large solenoid, and under this approximation, B inside is given by mu naught Ni. And direction according to right hand rule. Just curl your fingers. Thumb will give you direction of the magnetic field. So here we are assuming uniform magnetic field in this direction, where N is the number of turns per unit length, N by L into I. This is the field inside. And we are assuming field outside is 0. B outside we are assuming 0. So what is the magnetic field inside the solenoid? Magnitude you have to find. So this value is 4 pi 10 to power minus 7. N is 500 divided by 0.5 and current is 5 ampere. So this will be 4 into 3.14 10 to power minus 7 and just multiply with 10. So 5 will cancel out. This is 5,000. I have multiplied numerator and denominator by 10. Then this 5 will cancel out. And so this value is, this is 10 to power 3, 10 to power minus 4. And approximate value is 6.28 into 10 to power minus 3 Tesla. This is the field inside. So it's a case of solenoid. You must remember that when L is far, far greater than A, under this approximation, we are taking field inside to be uniform and outside field is 0. So I am considering an ideal type of situation. ठीक है? Now question number 11, you have a similar type of question. Now see question number 12. Let's see question number 12. It's a case of toroid. Toroid is when a solenoid bent in a circular shape, that becomes a toroid. So a toroid has a core of inner radius 25 centimeter and outer radius is 26 centimeter, around which 3500 tons of wires are wound. Current is 11 ampere. What is the magnetic field outside the toroid? B inside core of the toroid and C inside the empty space. So let's consider a solenoid is bent in a circular shape. So I am assuming just see. So this is the current. Solenoid bent in a circular shape. And this is R1 and this is R2. So we have to take the average radius. And in this, in ideal situation, here field will be 0, here field will be 0. In these two regions, field will be 0, that in the toroidal symmetry. So A part outside the toroid field is 0. C part in the empty free space surrounded by the toroid field is 0. Inside the core of the toroid, what will be magnetic field? Question number 12. So that is given by B inside. It is given by mu naught Ni by 2 pi r. And here this 2 pi r is the average length. R is given by R1 plus R2 by 2. ठीक है? Just give me 1 minute. संडे नहीं कल क्या 5th को मिलते हैं सैटरडे या संडे में बुला ठीक है एक्चुअली मेरी अभी क्लास चल रही है मैं बात करूं Let's calculate this value. So what will be average length that we have to find? Let's check this. This average length is given by R1 is 25 centimeter plus R2 is 26 centimeter divided by 2. So this is 51 by 2 centimeter. So this is 25.5 centimeter. So what will be 2 pi r? So this will give you 2 pi r will be 2 into 3.14 into 25.5 centimeter. So this will be 51 times 3. So if you multiply, let's say, so this value is, you should write it in meters. So let's see, this will be into 10 to power minus 2 meters. So that will be 3.14 into 0.51 meter. So B is given by 4 into pi 10 to power minus 7. You can take it as pi itself because here you have a pi, so pi will cancel out. So N is 3500 and 3500. Current is 11 ampere divided by pi into 0.51. ठीक है? So this will give you, let's calculate the value. So try to calculate this value. So if this approximate value is 3 into 10 to power minus 2 Tesla. Just check the numerical calculation. 3 into 10 to power minus 2 Tesla. Is it clear? So that will be field inside. And again, this field will be in the phi cap direction. This field will be in the phi cap direction. And in these two regions, field will be 0. Clear? Now we will see. Let's see some other question. Now see question number 14. Try to solve question number 14. So it's a square coil of side 10 centimeter. So you have a square coil of 10 centimeter consists of 20 turns and carries a current of 12 ampere. The coil is suspended vertically and normal to the plane of the coil makes an angle 30° with the direction of a uniform horizontal magnetic field of 0.80 Tesla. What is the magnitude of the torque experienced by the coil? So if you are assuming this to be direction of magnetic field B, and let's see, there is a square loop and it has, I'm assuming it has 20 turns. So let's say it has 20 turns and this is N cap. And this makes an angle 30° with B. So when you have a small current loop, it acts as a small magnetic dipole. So I'm taking this to be a coil having 20 turns. So what will be the dipole moment? Magnetic dipole moment is given by magnetic dipole moment M is given by N I A and direction is N cap. A is the area of the single loop. I is the current because there are N turns. So I'm taking it as NIA. And what should be the torque? So whenever a dipole is placed in an external field, it will experience torque and dipole will try to align in field direction. So torque is given by M cross B. So you have to find magnitude of torque. So that will be given by NIA B sine of 30 degree. So let's calculate this value. Number of turn is 20. Current is 12 ampere. Current is 12 ampere. Area is L into L. So this is side is 0.1 into 0.1. This is area and magnetic field B is 0.8 Tesla. Sine 30 is 1 by 2. This will be the torque. So what will be this value? This will be 10 times. If you multiply with this is 8 into 12 into 1 into 10 to power minus 2. So 0.96 Newton meter. ठीक है? This will be the torque. So torque is 0.96 Newton meter. When a magnetic dipole is placed in an external field, it will experience torque and it will try to align in the field direction. So magnitude of torque is this value. ठीक है? So now question number 15. Now you have a circular coil. Instead of square shape, it's a circular coil of 30 turn. Radius is 8 centimeter and carrying a current of 6 ampere is suspended vertically in a uniform horizontal magnetic field of 1 Tesla. The field lines makes an angle 60 degree with the normal of the coil. So calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. So you have to apply same torque opposite to the torque experienced by the magnetic dipole. So that will be given by B is given as same thing is only thing is now torque magnitude of torque is given by MB sine theta. M is given by NIA B sine of 60 degree. Sine of 60 degree and N is number of turn is 30. Current is 6 ampere. Area is, let's say this is, area is pi r square. Pi and r is, radius is 8 centimeter. So this is 0.08 meter whole square. This is pi r square. And then B is 1 Tesla. And this is under root 3 by 2. So you have to apply torque of same magnitude in opposite direction. And if you check this value, this is, let's calculate the value. So I think this approximate value is, just check this value, 3.13 nanometer. This will be the magnitude of torque. ठीक है? Is it clear? This will be the magnitude of torque. Now question number 6, you have to try. Now see question number 17. Question number 17. Try to solve question number 17. An electron emitted by a heated cathode and accelerated through a potential difference of 2 kilo electron volt. So first it is accelerated. So what will be kinetic energy gain? That is given by E into potential applied. And then it enters a region of uniform magnetic field. Determine the trajectory of the electron if the field A transfers to its initial velocity and B makes an angle 30° with the initial velocity. So in first part, what will be kinetic energy of the electron? Energy of the electron is half mv square, and this is given as E into V. V is the potential that is applied. So what will be velocity gain? Velocity gain will be given by 2 EV by m. ठीक है? And then in first part, determine the trajectory of the electron if the field is transfers to the initial velocity. So motion will be in circular path. So in A part, you have a motion is in circular path. Whenever charge particle enters perpendicular to B, you will get a circular path. And what will be radius of the circle? This is mv by EB. And then m by EB, V is given by under root 2 EV by m. So just substitute these values and then you will get the radius of the circular path. In this case, trajectory will be a circle and its radius is given by this value. Clear? So what will be mass of the electron? This is 9.1 10 to power minus 31 kg. Electronic charge is 1.6 10 to power minus 19. What will be magnetic field B? 0.15. So you have to substitute these values. 2 into 1.6 10 to power minus 19. And voltage is 2 into 10 to power 3 volt. This is in kilovolt. Mass is 9.1 10 to power minus 31. So it's a matter of calculation. So if you calculate this, this value is approximately 10 to power minus 3 meter, and that is 1 millimeter. So radius of the circular path will be 1 millimeter. Clear? Now in B part, let's see. You have to see when it makes an angle 30° with the initial velocity, what will be path taken by the charged particle? So in B part, this is the direction of magnetic field B, and it enters with velocity V, making an angle of 30°. So what will happen? Making an angle of 30°. So it has two components. One is V perpendicular. This is given by V sine 30. And this is V parallel, that is V cos 30. V parallel is this V parallel is V cos 30. V parallel is V cos 30. So perpendicular component will try to move the charged particle on a circular path. If there is only perpendicular component, then charged particle will move on a circular path. So if you take V cross B, so center will be inward. So when there is only perpendicular component, you will get the circular path. But V parallel will try to move in the direction of B. So net path, resultant path is a helical path. So in this case, you will get a helical path. This will be a helical path. Now what will be radius of the helical path? This will be given by, you have in this case radius of the helical path. Radius of the helical path. So that will be given by MV perpendicular by EB. So let's calculate this value. And MV perpendicular is V sine 30. So this will be given by MV sine 30 by EB. So now it's a matter of calculation. M is given by 9.1 10 to power minus 31, and V is so, and this is sine 30 is 1 by 2 E is the electronic charge, 1.6 10 to power minus 19. B is given by 0.15 and V is given by 2E. Just see, we have taken this 2 EV by M. So if you take 2, 1.6 10 to power minus 19, this is 2 into 10 to power 3 divided by 1.6, mass is 9.1 10 to power minus 31. So this will be 9.1 10 to power minus 31 kg. So it's a matter of calculation. Calculation you have to verify. If you check, let's take it as R1. Take this radius as R1. So this value is 0.5 into 10 to power minus 3 meter, or this is 0.5 millimeter. Is it clear? Now there are few more questions that is based on ammeter and voltmeter. So you have to solve this question. I will discuss it in next lecture. Okay. So try to solve question number 18, 19, 20 and 21. So that is based on ammeter and voltmeter. Okay. So we will solve this question in next lecture. So meet you in next lecture. Chalo. Thank you. Thank you everyone.